All right. So we got some people logging in. Appreciate you joining us this month for our Ask Mayfield Anything series. As people get going, I'd like to say, we're performing that, or we have this feature. We're asking people to, send in your questions. We'd love to get the interaction. What we do ask from that, though, is as we get going, if you can use the Q&A portion of the Zoom feature to submit those questions. It's just a lot easier for us to manage, for us to keep track of the questions. The chat feature is there, but it makes it more difficult. So Q&A is the best way to make sure that you're asking the question where we're going to be able to see it. So with that, welcome everybody. Appreciate your time as always. And so our Ask Mayfield Anything series, my name is Ryan Mayfield, founder of Mayfield Renewables, been in the industry since '99 now. And, we are happy to be bringing these folks on today to talk about power studies, importance of power studies, and just kind of going through what the process is for those and understanding, where to use them, when to use them, things like that. So that's going to be what we do. For those of you who don't know Mayfield Renewables, we are a technical consultancy. I founded the company in 2007, and part of what our mission is making education and information accessible for folks. So part of that is this AMA series, and so bringing on folks from ETAP, bringing on our system designers, so making it accessible for folks. And we do that through our engineering, system design and engineering, product consulting for manufacturers, and then also doing project consulting with EPCs. So if there's something that we might be able to help you with, feel free to reach out with us. Okay, so I want to kind of get jumped in here. So we have 3 guests here joining us today. We have Victor and Clayton from ETAP, and Nick Kirk from our team from Mayfield Renewables, one of our senior designers. So, real quick, I'm going to give everybody a chance to introduce themselves as well. But Victor he's a engineer by trade, been in the industry for 15 years now, and at ETAP for 12 years. So quite an impressive run there, Victor. But yeah, so why don't you tell the audience a little bit about yourself and kind of your, how you fit in over at ETAP.
Yes. Thank you, Ryan. My experience has mainly been on performing power system analysis, as well as developing, testing, and also training other power system engineers on how to use ETAP. Right? It's a tool in a lot of power system engineers' toolkit. It is used to make protection, coordination, arc flash calculations easier to manage, more efficiently, and to eliminate human error. So that's been mainly my background in simulation analysis and performing power system studies.
Awesome, great. Thanks for joining us. Happy to have you. Clayton, you bring your background from power systems and been in the industry for a while now. So can you tell us a little bit about yourself as well?
Absolutely. Thanks, Ryan, for having us. Yeah, my name is Clayton Bennett. I'm actually a systems engineer by trade, and I've been at ETAP, although a short while, but I support Victor and his sales team by providing demonstrations and educating EPCs and the general community about ETAP and how we can add value by saving time on running these analysis, among other value adds. But yeah, so most of my background is power distribution, and I've added the power systems background recently. So yeah, happy to be here. Thank you.
Awesome. And then Nick is one of our senior design engineers and been with Mayfield for a few years now. 2010, I believe, is when got started in the industry, Nick. And Nick's been doing PV system design specifically, and one of his roles that we've had him jump into, and he's been helping with are these power system studies. So we'll talk a little bit about kind of the motivation behind those. But yeah, Nick, why don't you, what did I miss?
Thanks, Ryan. Yeah, like you mentioned, I've been in the solar and energy storage industry for the past 13 years. I'm a senior design engineer at Mayfield, handling full construction plan set development on PV and storage and microgrid systems, as well as providing ETAP power system analysis services. I'm happy to be a part of this discussion and dive into how these studies can benefit renewable energy projects.
Cool. Okay, so let's jump into it. So, we're talking today about designing smarter, safer systems with power studies. And so I like to kind of set the stage very often in these types of webinars. And for us, the industry as a whole, really, we've been seeing a lot more of the need for power studies. It's one of those interesting things, we have the motivations here: safety, optimization, and code compliance. And within the PV and solar plus storage industries, I would say we've been seeing this need more and more. And so we've been getting requests from our clients. It's been growing over the years. And so it's been one of our motivations to get in to helping our clients with doing these. And then we, have a whole bunch of code references here. So for those of you that know me, code is my happy place. But you can see here, there's a number of different locations where arc flash, fault current, coordination studies, all these things show up within code. And then even in the chapters 1 and 2, we have requirements in 110, we have requirements in 240. So this isn't necessarily something that's new. I would say it's something that hasn't been maybe applied within the PV industry, maybe even as much as it should be, but we're definitely starting to see that change. And so working with partners like ETAP, learning these systems has been a big part for us in terms of some of the services we're offering and helping the clients make sure that they are code compliant and they are making sure that these systems are as safe as they possibly can be when we get into large scale PV systems, energy storage systems, and making sure that we're providing the best systems possible for the clients. So with that, I'm going to kick it over to Victor. And one of the things when we were starting going on this, I asked Victor to kind of give us the power system studies 101, make sure that we're all talking the same language. This is something that I feel like I'm learning a lot even in the conversations we've had preparing for this. And so hopefully you and the audience as well are able to gain a lot more understanding on what exactly these are, kind of what the reasons for them are, and what the different, different nomenclature, what it means. So with that, Victor, will you kind of walk us through these set of slides?
Yeah, certainly. Thank you, Ryan. I'd like to introduce just first, let's talk about a quick definition of what is a power system studies. Usually, the engineers I talk to, they define a power system study as just a requirement, right? I need to do a power system study to sign off on this project, pass the inspection. But in reality, a power system study is more than that, right? It's a set of engineering analysis. It's almost like an investigation, but the goal is safety. Safety for both human safety and also equipment safety. So everybody wants to operate a system that will outlive, right, the design life, and more importantly, to be safe. So power system studies help us get to that point, operate a safe system, reliable, right, reliable power. So if in the event, for example, there is a fault somewhere on a low voltage location, that we isolate the fault there. So a power system helps us add reliability to the power distribution system. So it's definitely more than just a requirement. So I think as we look at power systems more in the safety aspect, then I think we're able to do a better job and we're able to better justify, right, that it's important for human safety and it's important for the safety also of the equipment. So the power system studies, we could probably talk about 60 or more power system studies that can be performed, but the scope of work for today is going to be the bread and butter that most of us do on a daily basis. So these cover the conductor and equipment sizing, the short circuit analysis, and also the device duty evaluation, protection and coordination. Clayton will talk a little bit about DCR Flash. I'll tie it in with battery energy storage. And then Nick will cover underground raceway systems. So these are basic power system studies that you'll find on NEC, IEEE color books, and other standard and requirements. But they don't stop there, right? There's harmonics, there's transients, EMT. So we're just going to focus on kind of the bread and butter.
Yes, that's a great point. I kind of wanted to just make sure that we, talk about that just a little bit. So power system studies is kind of that umbrella term, right? It's there's a lot that comes underneath that. And so there's going to be specific things for our PV systems. And so understanding what those requirements are, what those needs are, is part of what the engineers need to be aware of doing these studies. Right. And so correct me if I'm wrong on ETAP specifically. ETAP, you can buy different modules. Is that correct? So if you're doing specific tests, if you were to do, you mentioned harmonics, which is not on this list, but that would be something that you would.
Yeah, you're correct, Ryan. The way that you use a tool like ETAP is you start with a base ETAP base license, and it includes the items that you see here on this particular slide, which we call the bread and butter modules. They're common not just for the renewable PV, but also on industrial, commercial, and even utility scale type of power system studies. And then from there, as your needs grow, right? Sometimes you have the need of doing power quality. That's where harmonics comes into play, especially when you have multiple inverters or variable speed drives. Those are a source of harmonics. As your needs grow, you can add modules to an existing ETAP license, anything from transient stability, right? If you wanted to see what would be the impact of a disturbance, like when your system goes on islanding mode, what would be the impact? There's a module for that. So as your team needs grow, so can your ETAP license.
Perfect. Okay. Yeah, I just wanted to make sure that kind of understood how that was.
All right, great. Let's go start talking about the conductor and equipment sizing. So the conductor and equipment sizing is actually part of the load flow analysis or a load flow study. And what it does is it simulates the power flow of an electrical system during when you're doing the design stage. And this is so important because it helps us size equipment such as transformers, cables, inverters, and very importantly, conductors, right? We want to make sure that we are, depending on the length and the load on the other side of the feeder, we want to make sure that we're sizing the conductors properly. So those are basic tools provided by the software. Additionally, right, it also helps check, right? Once you perform the design and you want to do a quick check as part of the this particular study, ETAP does have an equipment evaluation capability that gives you an alert when the equipment, so in this case, for example, a protected device, fuse, cartridge size, or frame on a low voltage breaker is not properly set, there will be an alert for that. Additionally, if you run a load flow, it'll give you any voltage rise or voltage drop alerts. And this is very common, especially on large PV systems with large DC collector bus. We'll usually, if you're not using the right inverter, you'll see a really large voltage rise. And that tends to cause all kinds of issues. So those are the type of alerts that you would be able to model and simulate at the design stage. So if there are mitigation steps that need to be taken to comply with, for example, NEC voltage levels, those could be done right on the design tool, on the environment, the ETAP platform, potentially saving thousands or millions of dollars on over budget or having to get new equipment once a site is built and commissioned. And then lastly, system losses, right? Because that's a big one. We want to run an efficient system. It's always a balancing act between how do I get the least amount of losses, because it's just like a other equipment. There will be losses through a cable, through a transformer, because of the internal impedance. So this platform also allows you to lower system losses either through switching optimization, or by sizing equipment properly, right? Let's go over the next study. So for the next study, let's talk about short circuit, and I put device duty evaluation in parentheses because that's the whole purpose of why we do a short circuit study. First of all, it's to protect the equipment, right? So we perform a short circuit study, not taking into account any protected devices. So we just simply take the impedance of the system, your cables, transformers, loads, inverters, PV, and we do a fault analysis. And then that fault is telling us, in the event of a single line to ground or line to line or line to line ground fault, what would be the amount of amps or kiloamps that we can expect for this location. And then we need to compare that against the equipment interrupting rating. So most of you are probably familiar with breaker interrupting rating or fuse interrupting rating, right? That's the KA rating that you see printed on the nameplate of the equipment. So whether it's a 42 KA or a 65 KA, what you're doing in a modeling environment like ETAP is when you perform your design and you select the equipment, every equipment has a library associated with it that you select from the software. So when you're doing a short circuit study, the software will automatically compare the calculated fault versus the interrupting rating of the equipment. So potentially making sure that the equipment is properly sized, right? And in the event of a fault, the equipment will function according to the manufacturer specifications. Because whether it's a line to ground fault or a line to line or a three-phase voltage fault, it's a huge release of energy. So we want to make sure that the gear and the protective equipment is properly rated. So that's the safety aspect of doing this particular study. So extremely important.
So with that, Victor, is that something? So you mentioned, the KA ratings, things like that. So does that require input from the utility? Do you need to know service size, conductor sizes, things like that, in order to properly get that information in to run these short circuit studies?
Yeah, that's correct. The input information is typically taken from like an AutoCAD file. Okay. So if you have a drawing in AutoCAD, that could be imported into ETAP. And there is definitely additional information that the engineer will have to enter, like the type of protected device, right? Whether it's a low voltage breaker, the manufacturer, the model. Other information that would need to also be collected is cable length, cable size, and very important, sometimes we overlook this, but it's also if we have a tie with the utility, right, what would be the maximum available fault that the utility or the grid that we are connecting to can provide at a given time. So this is collected directly from the utility. They are already used to this because industrial and commercial users ask for them, for this information all the time. But that's also important to know, because in the event that we have a fault on on the main substation, right, we're going to be getting contribution from not just the PV and the inverters, but we're also going to be getting a huge amount of contribution coming from the utility. So we add up both sources of contribution, and we arrive to the maximum available fault. And that's what we need to compare against the interrupting rating of the main protected device, or gear in this case, for example. And then just real quick to go over some of the sources of contribution, right? Because we talked about, contribution from the grid. If you have any rotating machines, so synchronous generators, induction motors, synchronous motors, pumps, for example, those will have, they would add to the contribution, the total contribution. Inverters will also have, right, even if they're smart inverters, if you look at the manufacturer provided data, there is some contribution that they provide as well. So all of these can be modeled in a simulation environment and design environment like ETAP, so that you can design the system safely, and you know exactly how much fault you can expect for a given location.
Real quick, I'm gonna, Drew had made a good point on a comment that he made. So these systems, those code sections that I pointed out in the beginning, most of those, if you read through them, they'll say, in other than dwelling units, you're going to go through and do these calculations, things like that. So really what we're focused in on are other than dwelling units. So small scale PV systems, this isn't something that you're really seeing. And so I guess, and then the question was, is there, is there any rule, or is there anything that would say that there's, systems that are in a commercial environment that don't need this, certain size or anything like that? Or is it pretty just cut and dry? Dwelling units, nope. If it's not dwelling unit, you're doing these per those code requirements. Do you know that, Victor?
Yeah, anything outside of residential. Residential is usually handled by your local utility or muni. However, anytime you're doing any type of commercial, industrial, renewable type of, like a PV farm, that is definitely a requirement, because you want to make sure that in the event of a fault, right, the equipment will be protected.
Sure.
Right, because if the worst thing that could happen is you have an explosion, right? You have a fault, which is basically an electrical explosion. The equipment is not rated properly, and instead of the breaker tripping, it just melts, explodes, and somebody gets hurt. Then OSHA gets involved, and we want to stay away from that. So anytime it's a commercial, industrial, or renewable site, yeah, this would be a requirement.
Okay, cool. Thank you.
All right, and let's talk about now the protection and coordination, which kind of ties into short circuit. So after we perform a short circuit study, we do protection and coordination. In fact, some larger utilities have an engineer that does protection, right? Their title is protection engineer. And the purpose of doing a protected device coordination, or PDC study, is to add reliability, isolate or contain the fault in the event that we have a short circuit. So if we look at the picture on the bottom left, you could see a system without selective coordination. And what that means is it's a radial system. So if you go all the way to the bottom, I have a yellow lighting bolt. That is the location where we have a fault. Maybe one of the cables, right, a line touched the ground, or two lines touched. Maybe somebody was working with a tool and it made a line to ground fault. In this case, you notice that there are multiple protected devices that trip. These are the red squares. Those are protected devices that opened. So if the system is not properly coordinated, it could bring down your whole system, right? A fault on the low voltage side can go all the way up to your main and essentially bring down the whole site, the whole operation. Where we want to be on the system that's on the right-hand side. Again, we're still on the bottom left with selective coordination. So if the study is performed properly and we have an incident, right? Again, the short circuit or the fault happens on the low voltage side all the way to the bottom of the system. It's isolated right at the gear or the switchboard, and the rest of the system remains unaffected in operation. So those are the green locations that you see. In a software or platform like ETAP, this is done graphically. So Nick is going to be going over a little bit more on the behind the scenes, the time characteristic curve, how it's performed. But the software does give you the ability to simulate a fault. So you could, for example, see there's an animation going on. There's a lightning bolt in red that is placed on the between a motor and a conductor, and you could see that number one starts to flash. That's the first protective device that would trip. Now, I want to build my system more redundant, so I want to know, in the event this protective device doesn't trip for whatever reason, right? Or if I have a fault on the line side of that device, what would be the next protective device to clear that fault? So that's number 2, and then obviously number 3 and 4. So that it's very unlikely that the first 2 will not trip, but just giving you a quick overview of what the capability of a software would be to look at multiple different operating conditions. So that is what the animation here is covering, just a sequence of operations when there's a fault somewhere in the system, and you as the engineer or the ETAP operator can actually place a fault anywhere in the system, right? So you can select, well, I want to fault the line side of an inverter, like the AC side of the inverter, the DC side. I want to fault right at a panel. I want to fault, on my main substation, and the software will go through the sequence of operations. So it's a very intuitive, very easy way to prove either to your customer or to the rest of your team, right, design team, what would be the impact of a fault in the system, how well it would be isolated. All right, let's talk. And Clayton, you want to briefly talk about the DCR Flash?
Yes, thanks, Victor. And real quick, I wanted to address, for high voltage, Victor, if we want to talk about kind of voltage level and what we support for Arc Flash for high voltage.
Mm-hmm. Yeah. So some renewable sites are extremely unique in the sense that we have seen large PV sites that, number one, have aluminum cable. So that alone makes them unique, because in commercial and industrial world that we see, it's always copper. And yes, we have a very large aluminum cable library in the software to model those instances, but also the other uncommon installation is gear, right? Outdoors gear, enclosed 34 or 34.5 or 35 kV gear. The Arc Flash AC standard, which is the IEEE 1584, currently only goes up to 15 kV, but ETAP has developed a method for calculating incident energy or producing these Arc Flash labels that you see on the screen on locations that are above 15 kV. Now, the importance of understanding what an Arc Flash study and what these labels are is the following. This is mainly just human safety. So Arc Flash is important because of human safety. We have had many different incidents. We've heard of many different reports over the years of, for example, an electrician opening a motor control center or a switchboard, switchgear, a panel, working on the equipment live and actually producing an explosion, what we call an arc flash. And an arc flash essentially is a release, a very quick release of large amounts of energy, basically almost like a fire, an explosion, an electrical explosion. So the labels are important because before the qualified electrician opens the equipment to do any kind of work live, they see the label. The label will say, warning, you must wear this PPE. The PPE is by categories like level 1 or category A, B, C, depending on the amount of heat the explosion releases. So you probably have, most of you know of like a 4-calorie, 8-calorie PPE suit. With things most all of us, when we're in the field, we're going to be wearing at least an 8-calorie, right? Which is the long sleeve overall, the shirt, the pants. However, there are locations, right, where the incident energy may be above 12, 24, 25 calories per centimeter square. And there's a different PPE that must be worn. So these labels let the electrician or the person working on the live equipment know before they open the panel what type of PPE to wear. PPE goes well above 100 calorie. It's basically like a spacesuit at that point, right? I think a lot of you have seen the spacesuit, completely fire retardant overall with the hood. Not a comfortable place to be, but it saves lives, right? We want to make sure that when that electrician or qualified person goes home, they go home safe to their family. This is a real danger, right? This explosion can cause severe burns, sometimes blowing the person many feet away from the equipment, bone fractures, loss of hearing because it releases a lot of noise, the loss of sight because sometimes it's so bright and there's a shrapnel that gets released during the explosion. A lot of people go blind, so we want to make sure that everyone is protected, and that's what the arc flash study accomplishes. Safety, right? Human safety.
Yep. Yeah.
So,
so.
And then Clayton, for DC, I know that we do a few methods, especially for PV installations.
Yeah, so Victor, just kind of want to go through kind of how you can use ETAP to mitigate those risks and really ensure safety and compliance throughout the system, your DC network specifically. So actually, DC arc flash and DC short circuit are two separate modules within ETAP. As Ryan discussed earlier, ETAP is modular. You can pick up different modules based on your needs. And these are actually two separate modules, but in fact are integrated together. As you can see on the picture there on the right, we can see a intelligent one-line view with arc flash and DC short circuit values displayed. So really what we're doing here is for many different applications, including mission critical facilities, substation, battery banks, PV plants, nuclear plants, transportation systems, among the likes. Really those are some of the main applications, but we're looking at the incident energy for direct current applications. Using these methods allows us to be fully compliant and ensures maximum reliability. And those include our maximum power calculation method, the Stokes and open launder method, as well as the Pockert method. And these are used in conjunction by ETAP to determine incident energy and shock protection boundary calculations. And then as we discussed, while all these are all NFPA 70E compliant, these help determine personal protective, PPE for workers. And ETAP does a really good job of, we have options for any kind of label you would need, specifically here to produce DC labels. We can also use these methods in ETAP to determine fault clearing time from DC protected devices. You can also model any sort of PV, batteries, chargers, UPS, DC motors, and AC-DC converters, among other inverter-based resources. As I mentioned, the DC arc flash and short circuit modules are integrated within the one line, and our biggest, probably most optimal way of utilizing the DC arc flash application is with our arc flash result analyzer. That's something that's basically accessible at, when running a study. You look at it in a tabular view and you can add any sort of report you'd like to the analyzer. And this helps you evaluate, really for us in the concern of safety and protection of our equipment. We're looking at worst case evaluation for incident energy levels. With ETAP, you can use this result analyzer to set up marginal and critical alerts throughout your DC network. And that's a really quick way of evaluating a DC system as it pertains to arc flash. Now I want to talk briefly about the short circuit module. And ETAP facilitates DC short circuit analysis to evaluate, the behavior of protector devices during a short circuit event. And some of the advantages of using ETAP is you're able to evaluate system fault conditions and assess protected device ratings for direct current systems. And these are all compliant with IEEE 946, also with international standards if you need that as well. You have the ability to not only look at, total bus contribution fault currents, but also branch contribution fault currents. You have the ability to look at fault current rising time, the peak fault current. As I was mentioning, we want to see the maximum short circuit compared to protected device rating, and as Victor mentioned. So looking at time constants and time to peak, and as well as steady state conditions, is relatively easy in ETAP. So having that visibility really ensures accurate analysis. And then lastly, just as I mentioned, modeling battery and chargers per IEEE standard is also a key feature within ETAP for DC short circuit analysis. One of the biggest things that, in my eyes, that really allows you to use ETAP to its full potential is the extensive library of DC equipment models that we have within ETAP. We have a extensive library of DC models for accurate analysis and simulation. Lastly, the ability to output detailed reports and visualizations allows you to make really informed decisions when upon running calculations for short circuit and arc flash within a DC system. So really, to kind of wrap things up there, employing ETAP's capabilities enhances your total system reliability and minimizes risk and just improves overall safety of personnel and equipment.
So I had a quick question. You mentioned some of the study or the types or the methodologies. So I feel like first time I looked at this was maybe almost 5-8 years ago, and when this was starting to come to at least into my consciousness. So on those, are those studies, I guess, multiple questions. One are, the methodologies, are those selectable by the user, and able to choose different ways of running through the methods? And then just the other part, how with it, and this was something that Chris kind of asked, and I think you just touched on it, was the library of data. So, are you able to build up a PV farm from known quantities, known modules, things like that, in order to quickly build that up?
Yeah, Victor, I don't know if you want to address the ability to user-defined methods for calculation.
Yeah, the calculation methods included in the software are three. The three that Clayton mentioned. There is So there is no IEEE or NEC standard
Right.
that is available for direct current arc flash, but we do use one that is extremely conservative. It's called the Stokes and Open Lander method. It's included in the program. This is user selectable, and it does take into account things like the distance between your electrodes, and it's extremely accurate. We have made improvements to this for PV systems. So you could be rest assured that, for example, the incident energy or the labels that are produced with this particular module are very close to reality.
Mm-hmm.
And trying to do a study like this by hand can be done. We have users that for many years did them in Excel spreadsheets, but the reason why they adopted a tool like ETAP is because instead of now their engineering team being able to do one site per week, now they're cranking out 8, 9, 10 sites per week. So it minimizes human error, but more importantly, it's productivity, right? Because you now have this powerful tool that allows you to be more efficient and shorten delivery time on projects and get more calculations on the same amount of time, essentially.
Cool.
So great question. We could briefly go over the battery energy storage.
Yeah, I was going to say we should move on. I'm trying to keep an eye on the clock.
Yeah.
I want to make sure we're give Nick a chance to talk
Yeah,
about putting it into practice and letting the audience see kind of how it goes into a PV system. So
yeah, up to this point, we've only been talking about, you know, a PV farm. As systems become more decentralized, or you have, for example, the need to model storage, there is the ability to model battery energy, perform analysis like battery discharge. Many chemistries are supported, lithium ion, for example, lead acid. If you do also like industrial work, you know, the battery side of a UPS, it's a lot of lead acid batteries. And yes, going back to the library question, there is a comprehensive library for everything from batteries to PV. The software allows you to connect the PV cells you select in parallel or series, smart inverters, protected devices, down to cables, right? Different manufacturers, and you just basically, like AutoCAD, you plug and play, connect them, and then just run your desired analysis. And then finally, next slide is the ability to design and simulate a microgrid, right? So as you begin to get into other renewable type projects like microgrid design and analysis, you could now take the same platform and do design of microgrids as well as perform the power system studies that we mentioned earlier. So that is also you know, a part of the solution with ETAP. And then we can wrap up with the next slide, which is the digital twin. A lot of engineering firms, they start with a conceptual design that is in Revit. A lot of times it's three-dimensional, for example. ETAP does have a bi-directional interface with Revit, with AutoCAD, Aviva Engineering, SmartPlan Electrical, as you could see on the screen. And then the digital twin is when ETAP is connected to a power monitoring or SCADA system, right? Operations. And the real value to that is, next slide, is on the connectivity to an existing network. Here we have ETAP on the right-hand side. That's the design and the analysis tool. It does have the drivers and the connectivity to connect to an existing metering network. This could be a power monitoring, a SCADA. We're vendor agnostic, and connect directly to equipment like protection relays. And using a module like eProtect, the protection engineer can read protected device settings, perform the study, the protection study we talked about earlier in ETAP, and then send out the protected device settings back to the protection relay. Again, minimizing human error and making your job a lot easier, right? With less errors. So that I just wanted to wrap
the
up.
file that directly.
Yep.
I was just saying it's a file that directly talks to the relay and it just populates it. That's awesome. Okay.
Correct. Yeah. So and to your point, Ryan, the connectivity doesn't have to be there. You could use ETAP to simply write the native file.
Oh, okay.
And then put that on your laptop, bring your laptop to the field,
Upload it.
and then upload it. Correct.
Perfect. Okay.
So I'll pass it over to Nick.
Okay. Cool. Thanks for that, guys. So real quick, Nick, before we get going, so somebody asked if they could get a glimpse of the DC library, and I'm the one running the show here, and I'm not smart enough to have ETAP on my computer, so I can't pull anything up like that. But I'm sure we can get you in contact with ETAP if you wanted to get some more information on that. So Nick, why don't you? So we've kind of gone through the different features of these studies, what we can do. And so this is something that we, Mayfield Renewables, have started doing, offering this service to our clients, being able to put this into play as for the system design engineering that we're doing. So Nick, you have a specific job that we kind of went through, and just so start walking us through what this looks like as you are applying it to an actual PV system.
Yeah, awesome. Thanks, Ryan. And thanks, Victor and Clayton. What we were hoping to do here is just demonstrate at the project level what a power system study can do for your project. And essentially, power system studies are essential tools that are widely used in traditional commercial, industrial, and electrical systems, but are becoming increasingly more important to DER system development. This particular project was a PV only installation. Our client came to us with 10 sites that they were developing and needed plan set design review, EE stamps, and power system studies. The goal of hiring on Mayfield was to help provide NEC compliance, protection coordination, and arc flash labeling. We met these goals by providing reviews on their 60, 90, and construction stage designs, and as well as performing these power system studies, which you'll see here. These studies are ideally performed around the 60% design. This allows us essentially the ability to know the design enough, but we are far enough in advance of equipment procurement. Ryan, next slide. The first study we performed was the Thermalampacity Study. And so this allowed us to take the developer's trench detail. And in this case, we originally had 8 inches on center between the direct buried circuits. And by using ETAP, we were able to model these circuits by taking into account this layout, the soil temperature at the desired conductor depths, soil thermal resistivity that we got from a geotech report. And we also included SAM modeling. The SAM modeling allowed us to produce a transient load profile so that we can account for the daily cycling of the PV asset. This basically, during the nighttime, the soil is going to cool off, and during the daytime, the soil is going to heat up due to the loading on the conductors. And so by accounting for all this, we were able to determine that this spacing is sufficient, and our end result was a max temperature of 33 degrees C. Further analysis was required, though. One of the sites had wetlands that they were installing on and around, and part of that requirement was to minimize disturbance. And so they came to us and asked to reduce the circuit spacing down to 3-inch on center, which you can see in that upper right picture. And the resulting analysis gave us a max conductor temperature of 40 degrees or 47 degrees C. And so our goal there is to stay under the insulation temperature rating for the conductor.
So real quick, when I first saw this, I was pretty fascinated by this whole thing. So we're looking at basically a month time frame, if I remember right. And so looking at the kind of worst case scenario, when the soil is the warmest, when the PV array is producing the most, and kind of what do those gains and losses look like? And so it's just interesting to me, kind of that curve to it, but then it levels off towards the end of the month. And so I don't know, when I saw that was something that I was just kind of fascinated by the whole thing.
Yeah, thanks for pointing that out. Yeah, so our analysis was over a 30-day time period, and we basically ran the study on a few different ways to determine where in the year the highest conductor temperature would be, because as we're aware, some really cold and sunny days in the springtime can produce a lot of PV energy. But because the average soil temperature during those months is pretty low, we found that the worst case was actually closer to the middle of summer for this particular site. It's all site dependent, right? So it's based on soil conditions, environmental conditions, and then all the inputs from the design that we're incorporating into the model.
Right. Yeah, that was the part that was like the geotech gets involved. So there's a lot to it. It's not just a matter of, running how much current are you getting through those conductors. So I don't need to hold us up. I was fascinated by the whole thing. Okay.
The next 3 studies, as Clayton and Victor indicated, they sort of relate to each other. We first, even before the Thermalampacity Study, we developed the ETAP single line diagram, which then later on in the course of the system design, we're getting submittals from our clients on specific equipment, such as the specific breakers, the switch gear, the transformer. We're gathering utility fault current. A lot of times the main step up transformer is going to be utility owned, and so we needed to know what primary fuse the utility was going to spec for the primary side of that transformer. And so we take all of this and we integrate it into our ETAP model, and then we can run the short circuit study, which will either verify or cause the need to change certain equipment through the system. And like I mentioned before, we like to do this at a certain point in the design so that we can capture issues before equipment procurement. And so in this particular case, on the right hand side, we're just pointing out the short circuit, the amps interrupting capacity of the specific devices, and then also the equipment ratings.
So this is taking existing equipment into account as well. So you're going to put in some existing equipment, and then we're adding PV to this in some cases. And so it's not always the case that we get to change, switchboard 1 or something, for example. It's like that's what it is, and we have to do the study to figure all that out, right? Is that what?
Yeah, exactly. In this particular case, we were modeling entirely new systems, but if we're adding PV or batteries to an existing facility, like winery or a wine storage facility, something like that, then we have to build this model based on what's existing.
What's already there.
Yeah.
Cool.
The next study was the protection coordination, and this is maybe a topic that may be a little outside of some PV developers' realm, and so I thought I'd just include the NEC definition. And so this is a localization of an overcurrent condition to restrict outages to the circuit or equipment affected, accomplished by the selection and installation of overcurrent protective devices and their ratings or settings for the full range of available overcurrents. It goes a little further, but I think that kind of captures what we're trying to do here. We're basically trying to prevent a fault that's lower down in the system from interrupting unrelated parts of the facility, essentially. And so ETAP software allows us to create these time current curves on the left-hand side here that allow us to properly coordinate the different overcurrent protection devices in the system. And then we're able, and once we've got that all built and coordinated, we can then verify it, like Victor showed earlier, by inserting a fault in a particular location. In this instance, I inserted one on just on the line side of inverter 3, and you can see that the first overcurrent protection device to trip was indicated there by the 1. That's the 162 amp circuit breaker, and then it went upstream from there. So the first one isolates the fault, but if for some reason that were not to interrupt, then it would follow upstream of the fault. And then the picture to the upper right there, that's just showing where these, so for a main circuit breaker, a lot of times we have several dials to set on the main circuit breaker. And in this case, we have instantaneous, long and short time trip, and ground fault. And so these settings that we get from ETAP would then translate into how we program the device in the field.
And just a quick, adding to this, the curves that Nick is showing on the left-hand side are preloaded with the software. These are the time overcurrent characteristics. So these are published by the manufacturer, and they tell the protection engineer, in this case, in the event of a fault, how long they will take to trip. So it's our job essentially to move the setting dials that you see on the right-hand side to make sure there is no overlap. So in the event of a fault, there is a spacing between them so that we know for certain that the system will be coordinated.
Thanks, Victor.
Excellent.
Yeah, and then the last study we ran here was the Arc Flash, and this once we have this model built, then we can run the Arc Flash analysis, and that produces all the information that would go on the Arc Flash labels, such as the incident energy, working distance, arc flash boundary, and required PPE for that hazard.
Excellent. Yeah, so I realize we're right at the top of the hour too, so I'm trying to be respectful of people's time and everything. There's definitely some more I think that we could go into here, and I see that there's a number of good questions that came in the last 5 minutes. So Amalia and Chris, I think we'll have to reach out to you directly to see if we can help you with those. But yeah, so this is, for me, this is a, kind of some of the key takeaways. Again, trying to semi-rush through these for those of you that have to jump off. But, NEC requirements are really driving a lot of this, the safety for people and for humans interacting, for the equipment itself. And then I think that one, Victor, that you mentioned a couple of times, minimizing the human error. And so being able to make sure that we are, not messing up, not forgetting to carry the one kind of thing, and having, missing some of this incident energy, some of these issues that might happen. And so ensuring that safe operation. So yeah, I guess with that, and if you guys have any final thoughts on these key takeaways.
I know it was a lot of information, but both Clayton and I are available. So Ryan and the Mayfield team, if there are any power system related questions that were unanswered, we're happy to take those offline. You could, send an introduction email. We'll be happy to answer any technical questions related to the items that were covered today.
Great. Thank you for that. And likewise, the Mayfield team, we're available. We like to, again, try and helping disseminate this information. And this is definitely something that we are seeing more and more and doing more and more. So, helping our clients out is an important aspect for us. So real quick, next month, Wednesday, August 23rd, we will be talking with Megger and Triforce Energy. We're going to talk about some O&M practices for PV systems. So mark that one on your calendar. There'll be more information coming on that. And so hope you can join us there. And then finally, here is contact information. So Victor and Clayton mentioned, if you have questions, you can reach out directly there. And then, of course, feel free to reach out to myself or Nick here at Mayfield Renewables. So with that, thank you. I'm sorry to I feel like I kind of rushed the end of it there. I feel like we probably could spend another 30 minutes here talking about all this. But I really appreciate your time, Victor, Clayton, Nick, and everybody in attendance. So yeah, thank you very much. And hopefully we'll talk to you soon.
Thank you all.
Thanks, Ryan. Thanks, everyone.
Thanks, Ryan. Thanks, guys.
Have a good day. Bye-bye.
Yes, you too.